So hello everybody, my name is Jan Georgiou. I'm working as CTO at RIX Technologies, and on behalf of the organizing committee, I would like to welcome you today to the 12th virtual edition of Kubernetes Athens meetup. So it has been a long time since the last Kubernetes meetup. It was held back in February. Among other reasons, we were waiting to see if the actual context, the COVID-related context, would allow us to host a physical event. But in the end, the waiting was too long, so we decided to go with a virtual. So yeah, unfortunately, we're not going to have the cool part, the social and networking part, and we're not going to have the pizzas and the beers in the end. But yeah, let's hope that this will come back some months from now, and we'll be able to do it again physically somewhere in Athens. In the meantime, we can see on the good side, an online virtual event can allow us to invite more lecturers from around the world and make it, you know, host their talks easier than before, and also broaden our audience. So people from everywhere can also join. So that's on the good side. Also, on another note, perhaps you can also see in the slides, we have a new logo. I hope you like that. We might make some changes, but it will stay in the same style. Okay, so that's with the general stuff. Let's go on the actual today's lecture. So I'm very happy today because we have invited my good friend Krzysztof. So he will be giving a more research R&D talk today. So Krzysztof is currently working as a lead data scientist at Google, and he works on the aspects of scheduling and resource management in Google Cloud. He is also associate professor at the Institute of Informatics in the University of Warsaw in Poland. And so today's talk is going to be upon Autopilot, which is a way to enable autoscaling at Google, and actually it works upon the predecessor of Kubernetes, which is called Borg, and is actually the internal orchestration engine at Google. So we're going to hear more about that right now. And Krzysztof, the floor is yours.
Thank you very much for the introduction. I just try to share my screen.
I think it should be fine
now. Can you see my slides?
Yes.
Okay, great. So again, thanks for the introduction, Yanis. Yeah, so it's December 2020, and you're probably as eager to end this pandemic year as I am. I talked with Yanis yesterday, and I understand you in Greece are in confinement now. So I'm very sorry to hear that. We are slightly better off in Poland now, but as we all know, this might change in days, and normally these changes are for worse. So anyway, I mean, there are very few good things this pandemic brought me personally, but this event, like being able to meet Yanis and then meet you all and give a talk in Athens, is one of these few good unexpected things. So I really appreciate this somewhat unexpected opportunity that I hope will be useful for you. So before we start with the talk, I will try to make this talk as interactive as only possible. I mean, given that we are separated by probably 2,000 kilometers of internet wiring, and we won't have this beer and pizza before and after. So remember, I mean, I'm not a podcast, so please be sure to post your questions by chat, or to raise your hands if you have any questions during my talk, and I will try to answer them as they appear. And actually, I'm very curious to learn your perspective on this work, because as Yanis said, this is something we use internally at Google. So probably the vocabulary and the model is slightly different from what you normally work with in Kubernetes, but I hope it's close enough to be interesting. Maybe let's try this hand raising. Please raise your hands how many of you would describe themselves principally as software developers. Raise your hands. All right, I see Yasilis. Okay, Tassos, George. Okay, thanks. And how many of you are more in DevOps or SREs? Also, please raise your hands. Okay, I see Nikos and Thanos. Okay, all right, thanks. Okay, so I'm going to present Autopilot, which is a tool we developed to automatically scale the workloads in the Google internal cloud. And Autopilot focuses on so-called high availability, latency sensitive jobs. So picture serving YouTube or Gmail to millions of end users. However, even if you don't work with YouTube or Gmail, or even if you don't work with serving jobs at all, the core problem, or how to set the limits for containers at runtime online, I think it's generic and applicable also in other infrastructures and other contexts. And what I really like about this topic is that it gives a very good snapshot of the current Google infrastructure. So, from our physical machines through layers and layers and layers of software infrastructure, to how we build our services to survive on this ever-changing and ever-failing infrastructure. This talk is based on a paper we had at this year's Euro-Sys conference. So the conference was unfortunately held virtually because it was going to happen in Greece, in Crete, in late April 2020, and I was very, very eager to visit Greece. Unfortunately, I couldn't. So this is, as you see, this is a joint work with many colleagues at Google, principally at Google Warsaw, where this system was developed. But these are only, co-authors of the paper. The system itself has even more developers who work on it during recent years. And the final disclaimer, I'm not by any means a Kubernetes expert. So the context for this talk is Borg. but I believe that the problems between Kubernetes and Borg are similar, at least in this area. And I'm, as I said at the beginning, I'm very eager to hear your comments or how you relate Kubernetes to what I present today. All right, so let's start. And I will start by taking you on a journey back in time. So imagine we are in 1999. Yeah, Matrix, the movie is playing in cinemas, and we are in the full-fledged .com bubble, and everyone uses Drop Shadow on their websites. And Google, still in beta, is booming too. We have exponentially increasing number of users of our search service, and we also use Drop Shadow on our logo. So imagine that this was what was behind this slick graphical user interface. So this is the first Google server rack that is now proudly presented in the Computing History Museum in Mountain View in California. And what you see here is that there are very few machines by modern standards. I mean, this number of machines probably now like runs probably a modern home or whatever, right? And if you have just a handful of machines, it's not too difficult to manage them. So we name them. We know what they do. They are just like household pets. A colleague of mine at the university has a small cluster of GPU machines, and I tend to use one of these machines for a course that I give in the summer term, where I teach my students GPU programming. So we have this resource management algorithm that we repeat every year. Basically, I call Marek, my colleague, on the phone and ask him something like, hey, hi, Marek, can we use Arnold as in the last edition of the course? And Marek responds, hey, you know what, Arnold is busy, but you can use Sylvester. And also, just in case, we have Chuck as a backup. Yeah, so now you can guess what is the naming strategy my colleague uses for his machines. But more seriously, if you were Google back in 1999, you could like statically assign your workload to these machines. Take a decision that, for instance, we run the crawler on the top 3 machines, and we run the database indexer on the bottom 2 or whatever. Now, fast forward 21 years, we are in 2020, we just survived 9 months of pandemic. We obviously, our logo is much cleaner. We got rid of the drop shadow, but the backend changed much more than that. We have dozens of data centers around the world, and this is what it looks like inside. So as you might imagine, managing this scale of resources is much more difficult. You can't just statically shard your workload to individual machines or individual racks. It is for many reasons. We have much more services and much more products than just search. These services, we no longer have a crawler or a database. We tend to have microservices that together function as a database, but these microservices are allocated separately. And finally, as you might imagine, the workload changes over time. So workload increases over time on a longer time scale as the internet increases. But there are also these usage spikes connected to some events. There are weekly cycles, there are daily cycles. So static amount of resources to, let's say, the user interface of Google search is simply wasteful. So we figured out very early that we have to automate resource management, and my talk is basically about this automation, how automation of resource management at Google is done. The first level of resource management at Google are containers. So in our internal cloud, job can serve YouTube, or a job can serve Gmail, or a job can be a batch computation, or a job can be my Colab or Jupyter notebook where I do some statistical analysis of virtual machine workload or whatever. But no matter what is the job type, to launch it on production machines, we pack it in a container, and then we ship it to 1 or 1,000 production machines, depending on the needs of the job. And the key feature of the real shipping container is this metal box that surrounds the payload. So this metal box protects the payload from the outside, from the weather, but also from the payloads of other containers, right? The impact, if you put in a container something that can be harmful, this harm should be limited to the inside of the box. Similarly, Linux container isolates the workload by setting limits on the maximum amount of resources that the processes running in this container can request. This is the size of the metal box. And normally the actual usage is usually lower, and what is left is slack, which is memory and processor that is allocated to this container, but idle because the container does not use these resources. And so now imagine that you're a Googler who wants to run a new service on our production machines. You know that you have to pack your job in a container, and you know that you have to somehow ship this container to our production machines. But how do you actually do this? Remember the scale of our resources. We have these racks and racks and racks of machines. So you can't just pick a random machine and SSH there and just start your container. You need to use a scheduler. So we call ours Borg. And this scheduler helps you to find the machine, but at the same time, it optimizes the usage of the infrastructure. And Borg uses container limits to pack containers onto the machines. And the rule is that for high priority serving jobs, Borg makes sure that there is sufficient resources on the machine to fulfill the requested capacity. So we do almost no overbooking for these high priority serving jobs. So as with shipping containers, again, you have to pack your machines by the size of the external box, the metal box, or in our world, the limit, and not the actual payload. So what you see here is a machine that runs 3 containers. And it turns out that the limits are just about right. They are slightly higher than the actual usage of the containers, but not like too high. So there are two kinds of problems with imprecise limits. First, limits can be too conservative, as on the left. In this situation, jobs are safe, but resources are wasted. The machine cannot accommodate any other container, but the actual utilization of the machine resources is low. So the resources are claimed but not used, at least not by this high availability latest necessity jobs. The other problem can be as on the right. Here we have a limit that is set to low for this yellow container, and the container claimed much more resources than so that the processes inside the container tried to claim much more resources than they were assigned, and this results in out of resources error. So the consequences of such errors depend on what is the resource type and what is the state of the machine. If the resource that is over requested is CPU, this container would be normally throttled down to its limit for some time, and when it keeps asking above its limits, it will be eventually killed, but it has some time to kind of reduce the usage. If it is memory, you can't throttle malloc, basically, the memory allocation. So you can only kill the processes running inside the container. So you can only hope that the whole job consisting of multiple containers has enough reliability, enough other containers running on other machines to not to fail completely, right? So overall, I mean, this is something that we really want to avoid. To add yet another layer of difficulty, limits in our internal infrastructure are fine-grained. So you request computational power for your tasks for your containers in units of millicores, so 1,000th of a CPU core, and you request memory in bytes. And here you see a cumulative distribution function for from our infrastructure showing distribution of requests for a large sample of our jobs. And as you see, our users really use this fine granularity. So there are no obvious steps. And in fact, someone computed that if we rounded up these millicores and these bytes to these nice looking round values that everyone in computer science loves, like 1 core or 2 cores, 4 cores, 8 cores, or 1 gig of memory, 2 gigs of memory, 4 gigs of memory, and so on, we would need much more machines to fulfill these resources. So on the one hand, I mean, you have a problem that you need to have these limits precise, not to overshoot because you lose capacity, not to undershoot because you affect reliability of your jobs, and the actual dials that you can change are very fine grained. So obviously setting this limit, if you're a software engineer or if you're a DevOps engineer, is really hard, especially if you have like not one or two serving jobs, but rather a dozen or tens of serving jobs that you have to monitor. You tend to be in a bit lost. So enter Autopilot, and basically Autopilot is a tool to automatically set the limits and the number of containers a job is running at. So it performs both horizontal and vertical scaling for Borg jobs. Autopilot is a controller, and it works in a standard feedback loop. We have these recommenders on the left that compute resource limits for each job. These limits are forwarded to Borg, actually to Borg master. So the schedule, the central part of the scheduler for a cluster on which the job is running. The Borg master forwards these limits to Borglets, or the part of the scheduler that runs on every machine, and Borglet sets these limits as cgroup limits for particular containers. And the feedback loop is closed because we continuously monitor usage data for all our jobs. We put it in a database, and then this database is read by recommenders. So the core logic here is in Autopilot Recommenders, and this is what I'm going to describe next. And I will describe like two main types of recommenders. The simplest type is the moving window recommender. Maybe let's stop here for a moment. Any questions so far, or like questions on how this relates to Kubernetes, or any ideas like why we designed Borg like this? Or okay, I see no questions, no hand raised, so I will continue. But please feel free to put your questions in the chat if anything comes out. So we have these two types of recommenders, and the simplest one is the moving window recommender. And this is basically simple time series methods to calculate limits. And this based on historical usage signal. So we take a moving window view of the signal. So there is this signal, and we run a moving window for, let's say, last 3 days or last 4 days, and we look at what happened during these last 3 days or last 4 days. The simplest method we use is just calculating, for instance, the 98th percentile of the signal falling in this sliding window. So then we smooth the response by exponential decaying the input. So this is because this is because we have if there is a sudden usage spike, we don't want to, like, when this spike falls out of the window, we don't want this sudden drop of the recommended size. We want to smoothly decrease the resource demand. Okay, I see two questions. Thanks. So Konstantinos asked, do you use Docker or LXC or something else? So I believe we have something specific to Google. I'm not sure what is it, because I don't work at this level, but probably this can be found in the Borg paper that I referenced at the end of the presentation. And the second question is, by jobs, do you mean applications or tasks? Okay, so a Borg job is a logical entity that serves a particular purpose. So, for instance, a job can be a front end to Gmail, or a job can be a database. A job can be a file system server, and the job is composed of multiple tasks, and the task is actually what runs on the machine, and the task is basically something like a container or a pod. Okay, and the next question is by Konstantinos. Do you take into account the programming language the application in the container is written in? Some languages uses memory in different ways. Yes, you're right. We do have problems with Java. Like, there is basically from our perspective, there are normal languages and there is Java, and and Java requires different handling than any other language. But this, we know what is inside. I mean, what language the software is running in the container is written in, so we can make this special treatment. Victor says everyone has problems with Java. Yes. Okay, so back to our recommender. So we have this exponential decay, and we are almost ready. We just add a constant safety margin to be on the safe side. And basically this in the black is what our moving window recommender would recommend for a job with this usage in that is in green. So this works quite well. And this already leads to significant savings of resources, and I will show the results later in this presentation. The only problem is that there are these parameters of this safety margin and the exponential decay rate, and basically these parameters have to be tuned for different jobs in a different way. So the result is that the DevOps engineer who runs the job does not have to set the limits, but they still have to tune the safety margins and the decay rates, which is still some manual process that you would like to avoid if only possible. And why this tuning is needed? Imagine that if a job has a very unstable usage, you normally add a higher safety margin than a job that has almost constant usage. On the other hand, if a job with a constant usage starts to ask for more resources, you usually want to respond quicker. So with smaller window size. Okay, so how do we solve this problem? We have these machine learning recommenders that use some simple ideas from reinforcement learning to automatically tune the parameters of this moving window algorithm. So internally, this machine, so what you see here is a model of a recommender for a single job. And this recommender internally runs many individual so-called models, and each model is a moving window algorithm. So the algorithm from the previous slide that has different parameters. So you see here two parameters. There is this safety margin on the x-axis and decay rate on the z-axis, and each model will pick a different limit according to its parameters. And on my picture, these limits are denoted in red. So, for instance, you can see here that the model with safety margin of 2% and decay rate of, say, 0.2 picked the limit equal to 1.1 gigabytes. And we have another model that has safety margin of 1% and decay rate of 0.1, and it picked a limit of 1.0 of 1 gigabyte. So then you have to pick a model, and basically we look at the behavior of the model, of each of the model in the recent past, and we pick the model that was the best according to rather complex and lengthy formula that takes into account, underserving, overserving, and the number of changes. But the key thing is that we pick a single model, and this model, which is denoted here in green, will drive the job for the next time period, a slightly longer time period, right? So say an hour rather than 30 seconds. Because we want to keep these models as stable as possible. All right, any questions for the models? Okay, I see no questions. Great. So let me pass to measurements. So we evaluated the performance based on observational study of jobs running in production, and these are these serving jobs, high availability serving jobs, and we focused on memory, as out of memory errors are harder to cope with than just CPU throttling. We measured efficiency, meaning how far are our limits to the actual usage, and we measured this using two different metrics. The first is the absolute slack, and this is just this is on the left, and this is just the difference between the total limit of the container and the total usage, and we sum this difference over a day. So this is a very ambitious metric, because like the absolute slack we would try to minimize the absolute slack, but the absolute slack of 0 will translate to the limit, which is always equal to the usage. Yeah, which is ambitious and probably impossible. We also measure the relative slack, and this is the fraction of allocated but unused resources. And here we use slightly different metrics for allocated and slightly different metrics for the used resources, because as allocated we take the average limit during the day, and as used we take the 95th percentile of the usage during the day. So I will show some results as CDFs, as cumulative distribution functions. So you read these plots in a way that you pick a number and then you say, for instance, 0 to 2, you on the x-axis, and then you go up and you see when this line going up from 0 to 2 intersects with the, or maybe you can see my pointer. So you start at a certain level of slack, and you check where this vertical line intersects with the curve, and then you see that, for instance, and then you go horizontally to the left, and you see that our machine learning recommenders, so more than 60% of the jobs have relative slack of 0.2 or less with our machine learning recommender. So what you aim here is, I mean, the ideal outcome would be a curve that goes vertically here and stays at 1.0 left. So you see here that the autopilot, both the moving window recommender and the machine learning recommender, result in significantly smaller slacks than jobs with manual limits, these dotted lines. The story with absolute slack, so this slack counted in as a difference between the limit and the usage, is similar. Again, we are much better with Autopilot ML and Autopilot moving window than the jobs with manual limits. And the unit here are machines. So here one is a memory capacity of a typical machine in a Google data center. So actually 80% of autopiloted jobs have absolute slack lower than 1% of a capacity of a typical machine. And the jobs with manual limits have larger slacks. And the totals, what you can't see in this picture, but it's possible to compute them, are impressive. So over 5,000 jobs in each category. The absolute slack of non-autopiloted jobs is 12,000 machines, whereas for autopiloted jobs is just 500 machines. And I see a question: how fast do the algorithm runs? How fast do the algorithms run to recommend a limit? Is it a constant time? So this was we made significant effort to make these algorithms fast and to to fit them on a small, let's say, standard machine, because you run these algorithms on all the jobs running on a particular cluster. So there are some parallelization tricks that are quite involved, let's say. Okay. All right. Another measurement. So the previous results might be affected by something called the confounding factor. Maybe autopiloted jobs are just easier to handle than manually driven jobs, or maybe they are smaller. So we ran another measurement. We measured jobs that migrated to autopilot in a certain month. We call this month here M0. We took a random sample of 500 jobs that migrated to autopilot, that started to use autopilot in this month. And we measured slack before and after the migration. And you see that before the migration, the average relative slack was 75% roughly. And the migration reduced the slack to just 20%. And the results for the absolute slack was very similar. But of course, Slack does not tell the whole story. We could have another recommender that just sets this limit to 0 and would have 0 Slack. So we need also to measure the quality, the reliability of the algorithm. And to measure reliability, we measure how frequent are the out-of-memory errors. And we weight the number of container terminations for a job by the overall number of containers in a job. So the story is that if you have a job that runs just 4 containers and we kill one of them, it's much worse for the job health than if you run a job on 100 containers and you kill 2 of them. So that's why we use these relative metrics. And out-of-memory errors are very rare. So you see here that we counted job day here, and with manual limits, we have 97, depending on whether the limit is soft or hard. We have 97 or something slightly higher than 98% of job days that are free, out-of-memory error-free. But the story for autopilot is much better because we are at 99.5% of job days that don't experience OOMs. So, in fact, when you take together reliability and efficiency, you see that autopilot is basically Pareto better than the manual limits. You save resources and you have less OOMs than manual limits. Some DevOps aspects. Currently, autopilot is used by over 48% of jobs at Google, counting by the capacity requested by these jobs. So, as you imagine, the impact is quite significant. And let me finish with a story. So, there was a service that had a new rollout, and it turned out that this rollout had a new version of this service. And it turns out that this new rollout had a small memory leak. And over time, as you can see, so this is a chart from our internal monitoring system that shows the limits and the usage of tasks for this job. So each task is a container, and this chart shows the usage of these containers over time. So you see that starting from 3 p.m., the memory usage slowly increases until it hits until it starts to hit the limit set manually at 2 gigabytes of memory. And okay, and the story is that this job was one of these manually driven jobs. So Autopilot, or these jobs, runs in so-called dry run mode. So we calculate the recommendations, but we don't actuate them. We just log them in this monitoring system. And you see that Autopilot would increase the limits a few times in response to this increased memory request. Yeah, but the job was not autopiloted. So it eventually at roughly 5:20 p.m., it started to hit this manual limit. So individual containers started to be killed by Borglets, and then restarted, and then killed, and then restarted, so on. So the job entered this crash loop cycle, and this job was, I mean, this is one of significant serving jobs, and so it had a team of DevOps engineers, on-call DevOps engineers, who, as soon as they saw these problems, started to work on resolving the problem, but it took them almost 2 hours to roll back the binary to the previous version. And just in case they increased the limits, let's say a bit after 7 p.m. But still, I mean, this almost 2 hour long outage was significant enough that the story was covered in newspapers and portals. So this shows that Autopilot is able to mitigate, would be able to mitigate the impact of such bugs. I mean, we can't increase the limit permanently, but the DevOps engineers could react to the increased limit and then do a rollback, rather than react to a job that is killed and then do a rollback, you know, when the whole outage is happening with oh my god, and then all right, so to wrap up, Autopilot. So I had two questions actually that I missed. How much is 48%? I can't tell you, and probably I don't. I mean, I can tell you that it's a lot, and it's I mean, it's significant. The other question by Athanasios is the Autopilot technology concept the same as the autoscaler in the managed GKE offering? Are there differences? Okay, I will answer this after the wrap up. So to wrap up, right? The Autopilot in general shows the gain that we can get from automating cloud resource management. Humans are bad at setting things precisely, and with Autopilot, the fleet runs more efficiently because the relative slack is reduced by a factor of 2. But additionally, these out-of-memory errors are also decreased. So we basically save these resources without consequences of decreased reliability. Probably the short conclusion is that if you have large-scale infrastructure, try to automate everything as aggressively as only possible. Okay, so if you have any questions, please put them in the chat, or you can ask them by voice. And I start by answering this question about GKE. So Autopilot, Autopilot is similar to, so the core problem of Autopilot is similar to the core problem of autoscaling in GKE, but the details are different, because in GKE and in other public cloud offerings, we have to be much more conservative with our clients' workloads than we can be on our internal cloud. In our internal cloud, I mean, jobs are programmed with the expectation that things will fall, that individual containers will be killed, and so the job itself has to be much more has to kind of fight against the falling infrastructure. With our client workloads, we try not to kill containers or pods, or not to kill virtual machines, unless there's like something really significant, like hardware failure on the machine that runs the virtual machine. So the trade-offs are somewhere different. And for the GKE offering, I'm not really sure what is the current state of the art there, but I mean, this is an area that we autoscaling for GKE is an area that we invest heavily, and we will continue to invest heavily in the future. Okay, and another question by Konstantinos is that we run without swap. Yes, we run without swap. Early on, we figured out that swapping is too unpredictable. When you start to swap, you have this time when you start to move things from the memory to the disk, and the serving jobs start to behave unpredictably in terms of response times. So it's better to kill a job and to respawn it elsewhere than to try to rescue with swapping. All right, any other questions? Yeah, so just like Kubernetes, as Konstantinos says. Any other questions?
You can also ask by audio if you prefer. Okay, I have one, Krzysztof.
Yeah.
How often? Yeah. First of all, thanks for the travel back to time and yeah, and the interesting talk, and also for the graphics with cumulative distribution functions. It has been long that I haven't seen them, so it's good to see. How often do you train the models?
So it is. So here there is no this, like, it's slightly different from kind of standard, let's say, neural networks, right? You have this crisp distinction between training a network when the network actually changes the parameters, and then just using the network when you just feed the data and check the numbers at the outside. Here, the distinction is not so obvious, because we rather than training and then checking the output, we rather continuously evaluate these models with new information from the usage data, and we make the decision to change the limit, let's say every now and then, in terms of, I would say, so seconds to minutes, rather than say days or hours. Okay, there is another type. Do you take into the consideration SLAs of application performance, like throughput, response time? That's a wonderful question. Our workload is so diverse that we would have problems addressing individual SLAs, because, like, you can imagine that different applications would have not only different SLAs in terms of numbers, like, one application would have let's say 95th percentile latency of 2 milliseconds, and the other would have of 100 milliseconds. But also some SLAs are, like, one application would monitor, say, 95th percentile of response latency, another would monitor, rather, let's say, the length of the queue of non-served requests, and yet another would monitor, I don't know, CPU usage, maybe. So we rather try to provide more or less certain performance, certain hardware, like virtualized hardware, right? Resources, like certain number of cores and a certain amount of memory, and we let the job to use this as efficiently as possible. And another question by Vasilis: how does Autopilot behave for applications with random spikes in resource utilization? it depends how spiky it is, this application in time. Probably we would try to cover the peaks of these spikes, and normally the time windows we use are long. We try to use, for vertical scaling, we rather use windows of 1 day, 2 days, 3 days, than let's say half an hour. So if we have sufficient history of spikiness, we would try to cover tops of these spikes. But if we don't, this application would and hopefully just one container would so one task would and the other ones would not. So the others could take the load of the poor guy that and was killed. But the limits are normally set for all the containers of the same job. So the limits would be adjusted to this spike we missed for this poor guy that was killed. Any other questions?
Is it, Krzysztof, is it currently in production at Google?
It is. Yeah. It is. So it depends. It depends on the category of jobs. So I presented that like roughly half of this high availability latency sensitive jobs use this in production. For batch workloads that I haven't covered at all in this talk, the adoption is even higher. But batch workloads are easier because, by definition, that you can kill containers there with less consequences than the serving workloads.
Mm-hmm. There is one more question.
Okay, thanks. I almost missed this by Thanos. What's such a concept be useful behind the scenes as serverless when workloads, lambdas or whatever, are suddenly triggered and need to scale to meet the demand? Yes, I would say so. The tricky part is that you need to with serverless, you need you need to kind of try to predict these spikes in advance and scale up in advance with serverless. But in general, I mean, this should also be applicable for serverless. Yes. Thanks for this question. Actually, I in my university job, I'm currently doing some research in scheduling serverless function executions. So, but I'm not looking at autoscaling, but rather at scheduling of individual calls.
So I suppose that if it's not used for every type of jobs, then it is not used for Google Functions, which is the serverless distribution from Google.
Yeah, honestly, I don't know. Yeah, because you in these Google Functions, you have the thing that you have the container that actually executes these serverless functions, and you have to size this container in a similar way to sizing, any other container. So theoretically, you could use such a tool. Yeah.
Yeah. Okay. Other questions? Okay, great. Perhaps we can, if there are no other questions, let me share my screen. Okay, so perhaps we can stop here. Before we go, just 2 more things. So we are going to continue. We are going to continue the meetups. We think that we will manage to do it every 2 months. So we are planning for the next one on 11th of February. This is going to be announced officially next week. And also, before we go, a big thank you to the sponsors, Qubit, Systems, Red Hat, Canonical, and RAX Technologies. And again, thanks a lot, Krzysztof. Looking forward to meet you again. Perhaps in an upcoming meetup, we can invite you here in Athens.
Yeah, I like this idea of beers and a pizza. Yeah. So can't mean, yeah.
Perfect.
Right.
Okay. Thank you, everyone, and see you.
Yeah, thanks.
See you soon.
Thank you. Bye.
Yeah.
Bye, everyone.